All right, friends. So the other thing that we do with parametrically defined curves is we talk about arc length. Arc length. So we have to imagine how the arc length process worked before and then just, well, do a little more of that. Here is a parametric curve, and we imagine that several line segments will do it for us. Each of those line segments has a length, and the length is based on a change in x and a change in y. And so what we're going to do is we're going to take a sum of the square root of delta x sub I squared plus delta y sub I squared. And this is how we started building an arc length integral long time ago. The problem is I want to turn this eventually into some kind of integral, and I want that integral to have a dt sitting right here, which means I need this sum to be a Riemann sum. And if it's going to be a Riemann sum, it's got to have a delta t sitting right there. But you can't do that unless you also divide by delta t. Everybody say, that's okay. Everybody say, how the heck are we going to scram with that delta t underneath? How's that going to, oh, I know how it's going to work, because we're not going to divide by delta t. We're going to divide by the square root of delta t squared. And that's going to let us do this. Without changing the value of our expression. And so what's going to end up happening, as what always happens when we're creating a definite integral, is we take smaller and smaller line segments that approximate the curve. We have more and more of them. We get infinitely many, infinitely small line segments. And what ends up happening, we get the square root of the delta x over delta t becomes a dx dt. The delta y over delta t becomes a dy dt from one time to another. That is the arc length integral. When I ask you for the arc length of a parametric curve, that is what I'm looking for. Here's the curious thing with that. In a motion context, if we were looking at Pete the particle moving in the plane, this would be Pete's speed. And so sure enough, if you integrate speed, you get distance traveled. All the stuff we used to know still works. Anyway, let's find the arc length. Let's find the arc length on 0 to pi over 2 for the curve x equals cosine squared t, y equals sine squared t. Let's find that. Arc length. Arc length is an integral from 0 to pi over 2 of square root of dx dt squared plus dy dt squared dt. Square root of dx dt squared plus dy dt squared dt. A little bit of simplification here. This is the square root of 4 blah bitty blah plus the square root of 4 blah bitty blah, but those are the same thing. So this is square root of 8 sine squared t cosine squared t dt. 4 sine squared cosine squared, 4 sine squared cosine squared, add them up. Okay, I got that. So this is radical 8 times the integral from 0 to pi over 2. Luckily, we're in quadrant 1, where the square root of sine squared t is just sine t, and the square root of cosine squared t is just cosine t. You don't have to worry about absolute values or anything because we're in quadrant 1, so that's good. And then all I have to do is know what is a good antiderivative of that. Well, it turns out that this is your u, because du happens to be, you're not going to believe this, the rest of it. So we have an antiderivative of u, and that's just 1/2 u squared from, oh, it's not from 0 to pi over 2. It's from the sine of 0 to the sine of pi over 2. And that is radical 2. Isn't that crazy? Come on, that's a little crazy. That's a little crazy. All right, one more. One more. Find the length of one arch of x equals 3 times t minus sine t, y equals 3 times 1 minus cosine t. By the way, they call this thing a cycloid. They call this thing a cycloid. I'll try really quick to show you why. Okay. 3 minus 3 cosine t is probably the easiest way to do that. We're going to go from 0 to 2 pi, because that's probably one cycle. Okay, and then there it is, and we'll do a zoom standard. Oh, no, that's not going to do it. We'll take our x's out to 20. There! That's one arch. That is one arch, and a fine-looking arch it is, if I say so myself. We should talk about what a cycloid is when we show up for class, but that's not important right now. What's important right now is that you know how to crank out an arc length integral. And an arc length integral is the integral from one time to another. 0 to 2 pi gets us one period of sine and cosine. That's going to be one arch of the square root of dx dt squared plus dy dt squared dt. Well, dx dt squared is 3 squared times the derivative of that thing. Oh, really? Really? I did this right. 3 times 1 minus cosine t squared. Then dy dt is 3 times the derivative of negative cosine t, which is positive sine t. And then you let your calculator do the work. Because for most arc length questions from the College Board, you are either just setting up an arc length integral, or you are working with something whose antiderivative is really, really easy to find, and that's not the case here. If they're going to have you find an arc length and it's not a straightforward integral, it's going to be calculator active, and so we've got to know how to do that. Okay. So no need to leave you with an OYO, just want you to make sure that you can do these problems, because arc length is going to pop up on the AP Calculus BC exam, and I want you to be able to do it. All right, so that's where we are. We'll see you tomorrow.